What I'm talking about today is a project that we have been working on for quite some time to develop heterodyne spectrometers for high-resolution emission line studies. This has been a much more general program than CubeSats or smallsats, but these instruments turn out to have significant utility for small satellites, and so I would like to sort of present the background of them and then sort of demonstrate where we're going in terms of developing them for small satellite applications where we will be able to achieve the kind of sensitivity and spectral resolving power that people normally associate with shell-like spectrometers on large telescopes. So I think there's a lot of potential there. Next slide, please. Yep. So just by way of some background for where we're working, we do fly spectroscopic instruments on robotic probes, and these are generally much smaller instruments than the sort that you see at a ground-based telescope. And a good example of that is, say, the ALICE spectrometer on Rosetta or the Virtus spectrometer. And these are small because they have very severe mass and volume limits on remote spacecraft. Not as severe as CubeSats, of course, but still fairly severe. And they are sensitive instruments not because they have a big telescope, but because they have a large field of view. And because they have a large field of view, their resolving powers are typically quite small. So I have on this slide an example of a spectrum taken by ALICE at Comet 67P, and you can see the aperture in the shape of the spectrum at right. And essentially, these instruments are capable of detecting the presence of a atomic or molecular species, but they tell you very little about the dynamics of what those materials are doing in the spectrum. Next slide, please. So at high resolving power, you get a lot more information. What I'm showing here is a spectrum of a different comet taken invisible, and the molecular species C2 in low resolving power at upper right. You can see the bands, and there's phantom structure inside the bands. However, look at it with a high resolving spectrometer, and the left axis is a spectrum obtained at the Keck telescope. You see that the individual band heads are broken out into rotational and vibrational bands. And at this type of resolving power, you can look at the individual transitions of the molecule, and from that you can get information about temperature, isotopic ratios. This is rich and set up Y. So that richness starts to come out when you can increase your resolving power. Next slide, please. Another example is the Jupiter system, and specifically Jupiter's moon Io, which is surrounded by a cloud of sodium vapor and also a torus of high energy plasma that is rotating very quickly with respect to the satellite and Jupiter. This results in an incredibly dynamic environment that we have very little information about, aside from the populations of the individual species. But if you look at the sodium in the clouds around Jupiter at high resolving power again, and this is an observation that we took using a spectrometer with resolving power about 2,000 to 3,000 times higher than what ALICE achieved, you start to see multiple velocity components and complex structures from turbulence inside the system. And so these types of diagnostics have just never existed for robotic probes. Next slide, please. So if we could achieve having high resolving power spectroscopic capabilities, we'd be able to identify many things, focusing primarily on solar system applications, but you can definitely use these in astrophysics, heliophysics, and also laboratory applications, although that's irrelevant for CubeSats. We're able to resolve a host of non-thermal processes, such as photochemical access from destruction of molecules, mass loading in plasma systems, charge exchange processes, plasma wave propagation. We can study atmospheric effects like auroral processes, ionospheric energy deposition, heating, turbulence, field-aligned currents, and also look at isotopic ratios. Really, it's a huge, huge scientific parameter space that is generally not exploited except from a remote ground-based perspective. And so the question is, could we give this type of technology to robotic craft, and specifically, can we get it into small sats, which would be truly groundbreaking because of the frequency of the opportunity. Next slide, please. So to understand why this hasn't happened up to now, it's important to understand why high-resolving spectroscopy, at least in the classical sense of using an Echelle spectrograph, is such a problem for remote spacecraft. And the problem comes in with the etendue of the instrument. The etendue is a very simple term. It's really a measure of the effective collecting area of the telescope feeding the spectrometer and the field of view of the entrance aperture of the spectrometer itself. When you multiply the product of those two together, and what you're getting is a measure of its overall sensitivity. So the higher your etendue, the more sensitive your instrument is. So the problem with high-resolving spectroscopy comes in with the fact that a field view of the entrance aperture directly relates to the resolving power in the sense that the spectrometer images that aperture at its exit, and your ability to separate images of that aperture is then your resolving power if your source fills your field of view, which it typically does for robotic applications. So, as a general rule, if you have a large effective area, you can have a small field of view, or if you have a small effective area and a large field of view, you have generally a large enough etendue to do solid astronomy. However, if you have both a small effective area and a small field of view, you will always have small etendue, and your instrument will not be sensitive. So at the bottom of this table, I show some examples. The bottom three are Echelle spectrometers located at the focus of fairly large telescopes. Keck is a 10-meter. HST is the smallest at 2.5 meters. And then the VLT is sort of intermediate between those. And you can see that those entrance apertures are quite small, 8 by 0.7 arc seconds. In the case of HST, it's 0.2 by 0.2 arc seconds. And UVES is 8 by 0.5 arc seconds. By contrast, if you look at ALICE, it had a very small 16 square centimeter area that's trivial compared with these other instruments. But its entrance aperture is 6 by 0.1 degrees. And as a result, its etendue is more than a factor of 30 greater than any of these other instruments. And therefore, very sensitive to very faint emissions, but only at a very, very small resolving power. And that really is the entire problem with getting high resolving power into these spacecraft, is that you need these small apertures to separate things spectrally, but you can't rely on the small apertures that you can fly either in a CubeSat or even on a robotic probe. Next slide, please. Yep. So this sort of illustrates where we are. From spacecraft perspectives, we either have to rely on use HST, which is always very remote from where we are looking, or we can build low-resolving power spectrometers that do fit in a CubeSat format. And in fact, the upcoming Lunar Ice Cube mission is going to incorporate a low-resolving power infrared spectrometer. And so this is definitely happening in CubeSats. What I would like to see happen, what we've been working toward, is to take that capability from Hubble and put it into a lunar ice cube class spacecraft. Next slide, please. Now, the direction that we have gone is to explore achieving high resolving power using interferometry. So interferometry, in a basic sense, does not operate by dispersing light with a grating and then re-imaging an entrance aperture. Instead, what it does is it interferes light with itself in the internal optics and creates a pattern of interference that is either directly related to wavelength or can be recovered using a Fourier Transform. There's two types that have been used for astronomical applications. In the first case, it has actually flown in space. The first is a Fabric Pro interferometer, which is an Heterodyne technique. And the picture at right shows a fairly large but still space-worthy Fabric Pro interferometer. These devices can have very wide field of view, as much as a degree in diameter or more, which means that they can be operated without a telescope and have more sensitivity than the spectrometer at the focus of the 10-meter Keck telescope. Next slide, please. Another option is the Michelson interferometer. Michelson interferometers are Fourier Transform devices. They can also have very large fields of view and can step through wavelengths using a scanning technique. And they operate by measuring the path difference between a stationary and a moving mirror. These instruments can scan over a very large range and can have also extremely high resolving powers of 100,000 to 1 million, which can give you very, very precise measurements of structure inside an emission line. Next slide, please. So the advantages of interferometers are that they do not require a telescope to have large etendue, and they can have very high resolving powers, like I said, and both Fabric Pros and Michelson interferometers can probably be made compact enough to fit inside a CubeSat. The disadvantages are that in their classical design, if one is hoping to get very high resolving power, the precision of the optical surfaces needs to be very, very high, which means that they have to be maintained thermally and mechanically such that there are no distortions. The placement and movement of those mirrors is very critical. Vibrations and thermal variability inside the system can wreak havoc with the resolving power. And all of these sensitivities scale as you go up in resolving power or inversely with wavelength, which means high resolving power and high sensitivity in the shortest wavelength ranges is generally not possible. So when interferometry has been used in space applications, it's generally used in the visible, but for the or, and this is probably much more common in infrared and intermediate resolving powers. Right, next slide, please. Yep. Okay, so our instrument is we call a Spatial Heterodyne Spectrometer. And it's a very simple laboratory application here that can sort of already show you that we are getting into compact format even without trying. The mold patterns on there are spaced by about 1 inch. So this is already a 3 to 4 U type of device without even attempting to make it compact. These reflective heterodyne spectrometers are able to sample the full resolving power of a grating while still having a very large intrinsic field of view. So they are comparable to the Michelson and Fabric Pro techniques. Not quite the same etendue, but they have a lot of advantages. Like those others, they don't require a large telescope, and as you can see, they can be made compact. Next slide, please. It's going to be a little challenging. I'm going to ask you to press a button, and we're going to step through The way these operate is light comes in and hits a grating button. It's symmetrically dispersed into two beams that transfer between two mirrors. Button. Okay, you might have to just advance through a couple because I can't even see what you're doing. So, in any case, what happens is as you move all the way through, the light returns to the grating. It's separated spatially with a roof mirror, and beams recombine and then exit the interferometer. Now, by setting transfer mirrors to a certain rotation, you can set it so that the wavefronts of the emerging beams at one wavelength are parallel to each other and do not interfere. However, all other wavelengths will have a counter-rotation that results in a rotation of their wavefronts as they exit. And the rotation becomes larger as the wavelength separation from your tuning wavelength increases. And as a result, you have a steady accumulation of path difference. You should probably just advance that all the way through and then go back. Did you go to the next slide?
I think we got it. We just the one before the table.
So what you wind up then with is a image of linear fringes, and those linear fringes can be Fourier transformed to recover the individual wavelengths coming inside the experiment. So the advantage of this is we don't need any moving parts for it. We set it and we go. Next slide, please. So this has many advantages. They don't require moving parts. The interference plane formed by this is very forgiving, so think optics can move, and it's still images, very high contrast. They're very sensitive to extremely small scale optical distortions on mirrors, but that's typically not the problem with surface quality. They've demonstrated a lot of mechanical and thermal stability, and that makes them very good for more extreme environments than the average interferometer. And they're very good for measurements of a single emission line feature. And the most exciting thing about it is that we've been able to demonstrate that these are stable with low quality optics in extreme environments all the way down into the extreme ultraviolet where interferometry has never been done in astrophysical context. And I've added our RSHS instrument to the table I showed you before with an even smaller collecting area than Alice, about a half degree by half degree field of view, and you can see that it has a higher intendue than CAP. Can you skip 2 slides, please?
Yep.
Okay, so at this point we've developed several laboratory versions. You can see that these are not terribly compact, and we've used them at telescopes to demonstrate the fundamental technique. And next slide, please. But more recently, we have constructed a version that has flown on a suborbital sounding rocket experiment with an interferometer aligned to the Lyman alpha line of hydrogen at 121 nanometers. So this is as short as anybody has done interferometry in space. The rocket is shown at left, and the interferometer is shown at right. This is still a fairly large instrument. It was able to hold alignment stably through the entire flight. During re-entry, it hit, landed, was shipped back to our laboratory, and still held alignment, so it was very stable. Next slide, please. We're reflying this rocket next year, and for that, we are going to fly, shoving it into the corners of the focal plane, a prototype for a CubeSat-ready version of the SHS that is going to be about a 3U-sized object. And so we are in the process right now of doing the mechanical development for that. And once we demonstrate it, we feel the technology should have a high enough TRL for mission applications. Next slide, please. And we're currently working to develop a design for this targeting a heliophysics technology demonstration program with modest payload budgets for a 12U class CubeSat that would include a 3U version of the SHS that will look at interplanetary hydrogen, so the diffuse background in the solar system that's been perturbed at the heliopause. And the selected mission would launch with IMAP and be taken out to the L1 point, where it would operate for 1 to 3 years, mapping the entire sky. And I'll stop there.
Okay, great. Thanks very much. Okay, so any questions, and I'll relay them through to what.
You said the spectral range was limited. How limited is that?
So the question is, you said the spectral range is limited. How limited is that?
Yeah, it's it depends on your resolving power. Since each wavelength segment is defined by a different number of fringes to the focal plane, your wavelength range is directly equal to the number of potential fringes that you can resolve at your detector, which is essentially the Nyquist limit of your detector multiplied by the number of pixels in the fringe direction. At very high resolving power, it can be quite small. It can be effectively a notch filter. So our sounding rocket experiment is of order 8 to 10 angstrom bandpass. However, it's possible to get much larger bandpasses out of this, and in fact, we're exploring that. I didn't have time to go into it, but actually, if you wanted to move down a couple of one slide, we're looking at 2 ways that we can achieve that kind of much larger bandpass. The 2 ways that we've been exploring is, one, to dynamically tune the mirrors so that we can reset the central wavelength of the tune to different wavelengths across a broad band. And so far, we've been able to demonstrate that this works over fairly large wavelength ranges, maybe a factor of 2 relative to some central wavelengths, say, for instance, 2 to 5, 6,000 angstroms. And this doesn't cost you as much as you would think, because in a Fourier transform, you will push noise from all your spectral features into all the other spectral features. And so being able to do this at isolated bands can actually give you a good performance. And the other option is to use order degeneracy inside the grating and simultaneously expose multiple orders at once. This can give you really wide band performance, and we're still exploring how to make that work. I know this will answer, sorry.
That's great. Next question.
So, according to the optical design, I understood that in fact your interferometer is like a Fourier Transform Heterodyne Spectrometer, and the properties are quite similar. We have made studies and have seen issues concerning the stability of such instrument. So maybe I'm wrong if I see the results with the Fourier Transform Heterodyne imager, but if not, then I would like to understand the difference.
Did you hear it? Or?
I really couldn't hear it well. There's a little bit of...
That's okay, I can repeat it. So the basic question was that there was a strong resemblance with a Fourier Transform Heterodyne imager, and preliminary studies on that have suggested there are issues with the stability. What do you think about that? Or do you know?
Actually, you're totally correct. You can do the same thing with this. We're just operating in the spectral domain as opposed to the imaging domain, and there's a way to actually make these instruments image instead of doing spectroscopic measurements. It's a more challenging technique because we actually have to move our field across the interference pattern in Fourier Transform the time domain brightness of the individual image elements. And that is a stability problem. You have to know exactly where you are at any given time. What we have found with this spectral technique is that it's far more stable than frankly, we ever thought it would be. We only decided to go down into the extreme UV after we flew our sounding rocket and began to notice that we could find no optical distortions inside the system. It is true that if you have active vibrations at certain resonances during exposure, you can begin to wash out the contrast of the fringes, and that we've seen that in some circumstances. But yeah, I do know what you're talking about, that there are stability issues. But I feel very confident that because we aren't moving anything and we're not operating in the time domain, that there's a lot of opportunity for finding ways to extract high performance out of these instruments, even in a relatively harsh environment of the CubeSat.
Okay, any further questions? No, well, thank you very much, folks. I'm sure Michael will say goodbye. But